Danilo, ci sei? Possiamo partire?
Sì, ho parlato a microfono spento. Ok, welcome to the IPROMO session of this afternoon. We will cover the climate change and natural hazard topic. The lecture will be held by Daniele Giordan and Niccolò Dematteis and myself from Italian National Research Council, particularly the Research Institute for Geohydrological Protection, and again, particularly from the Geohazard Monitoring Group. The lecture will be covered by 3 slots, and then there will be an update concerning the last events that interested our region in the weekend. That is unfortunately perfectly fitting the topic of today's lecture. Okay, now we will start with Daniele Giordan, please.
Okay, so good afternoon or good evening to everybody. I'm Daniele Giordan. I'm a scientific researcher of the Italian National Research Group, and I work at the Research Institute for Geohydrological Protection. There is one of the research institutes of Italian National Research Council that work in particular on topics related to geohydrological protection. That means landslides, debris flow, glacial risk, and rivers, in particular on floods. Of course, we work on research topics, so we are a scientific researcher, but our research institute is also a competence center of the National Civil Protection Agency. That means that in many during the last 10 years, more or less, we had the opportunity to work as scientific advisor of the National Civil Protection Agency, in particular for landslides, but also for other national emergency related to geohydrological protection. Danilo, Niccolò, and me work together in this geohazard monitoring group. There is a scientific research group that works in particular on the development and the use of monitoring system for the geohydrological processes, analysis, and monitoring. We work we work in different parts of Italy, and the focus of the lesson that I would like to propose today is some elements related to the effect of and impacts of climate change on geohydrological protections. Sorry, on geohydrological processes. I'm trying, okay, sorry. So this is a very, very important and large topic. It's not easy to analyze all the elements. In my lesson today, I would like to concentrate the attention in particular on slope instabilities and of course on mountain areas. If we consider climate change, of course, we have to consider some main effect of these that are clearly evident, in particular in mountain areas. That, of course, first of all, the rise of temperature, a different distribution on rainfall and snow, and the event occurred a few days ago in the south of Piemonte, Liguria, and the south of France. Probably is one of the last evidence of this trend in change of the distribution of rainfalls. In particular, in very high elevation areas, we have also, in particular, changes in the distribution of permafrost and also in the presence of recent deglaciated areas. Of course, this effect of the climate change has an incredible amount of impacts on our life and on our settlements. And we can consider for the topic that I would like to present today, in particular, the increase of flash floods that in next slide.
Daniele, excuse me.
See?
Can you hear me? There are some issues concerning your volume.
Okay. I have to
C'è audio e video,
sì.
impostazioni, altoparlante e microfono, penso puoi alzare il volume.
Sì, è troppo basso?
E mi dicono che è basso, sì. Sorry, it's easier to explain in Italian, so...
Sorry, I'm trying to... Now is better? Or is the same?
It is increased, at least. For me, it is increased.
Okay. So if it is good, I can continue, or...
Yes, please.
Okay.
Thank you.
So the some effect and impacts that I would like to introduce now. So a different distribution of debris flow and floods, an increase of flash floods, more slope instability due to permafrost reduction, and also an increase of glacier-related instabilities. I don't know. Okay. So in particular for mountain area, we can make a link between the rise of temperature that in many cases created a favorable condition for the construction of new settlements and a sort of colonization of new areas. That means that new areas are available, in particular in last decades, also for the creation of new ski area or new accommodation or other touristic activities that in many cases create also an increase of the level of risk. So we have the possibility now to make this sort of colonization of new areas, but the opposite side of the same medal is that in many cases we are rising the level of risk, in particular with an improvement of the vulnerability related to a high exposure of many areas. Also, for this increase of the number of slope instability and the number of geohydrological processes. One of the examples that we can present, and in particular my colleague Niccolò Dematteis will present in the last part of this lesson, is related to the Plampensee Glacier. Just to give you some words about these case studies this case study that will be presented later. We are in the Alpine region. In particular, this is the Mont Blanc Massif, and this is the Grand Juras. And one of the glacier in this area is characterized actually by the presence of an important instability of the glacier tongues, but the problem is not only the presence of an instability. The problem is that in the bottom of the valley, there is a very famous touristic valley. Okay, so the audio is too low. I have to, sorry. I'm trying to, I try to improve the audio in this way. Okay. Okay, so tell me if the audio now is okay. Just to continue with this example, this is the Plampensee village in the bottom of the valley, and this is a numerical model about a possible snow and ice avalanche due to the collapse of the frontal part of the Plampensee Glacier. That means that as I will present in next slides, the problem of the risk related to slope instabilities, of course, is not only related to the presence of this instability, but probably also to the vulnerability. I don't know if these elements are known, and for this reason, I would like to introduce some aspect of this this simple formula. So when we have to make a risk assessment, so an evaluation of the level of risk, we have to consider two main elements: the hazard and the vulnerability. In terms of hazard, we can say that, in particular, if we consider natural hazard, we are considering the probability that an unexpected or an uncontrollable natural event of defined magnitude could occur in a particular period of time. On the other hand, the vulnerability is a sort of evaluation of the potential loss. Okay, that means that the risk related to an area have to consider both the natural event, but also the element that can be considered a possible vulnerability. This, I believe, is very important because in many in different parts, I have the possibility to work, of course, in different parts of Italy, but not only. And we are very often concentrated, in particular, on hazard, so on the natural process. But sometimes we are not so sensible in the evaluation of the vulnerability. So I believe that is very important for people that have to manage some issue related to the environment that in many cases, in particular in many cases that I would like to, that I will present in my presentation today, can be managed only with the reduction of the vulnerability, because, for example, like with the Plampensio instability, it's quite impossible to stop this very large instability. So in many cases that are related to slope instability, it's not possible to use systems that are able to stabilize and so to reduce the hazard. And the only way to manage the risk is a reduction of vulnerability. And I believe that this is an important point because, of course, this sort of colonization of new area that can be done also as an effect of the climate change have to be done very careful, because in many cases we are increasing dramatically the vulnerability of our settlements. Three other important concepts that are related to the vulnerability, probably you know, but just to fix some points, there are exposure, sensitivity, and resilience. In particular, resilience is now an important topic that very considered, because we are probably changing our feeling towards I hope we are changing our feelings towards natural hazards, and that means that it's quite impossible to consider, in particular, a mountain environment with a risk zero. We know that there are the presence of many different natural hazards, and the only way is the only way that we have is to find a solution for correct behavior that reduce our vulnerability to this natural hazard and improve the resilience. So improve the capacity of the our social system to respond and recover after other events. In this presentation, I would like to focus in particular on slope instabilities, of course, in high mountain regions, describing the three different kind of slope instability. There are landslide, debris flow, and glacier instabilities. The glacier instabilities in particular will be the main focus of Niccolò Dematteis' presentation. So first of all, since I'm not sure that all of you are familiar with landslide, I would like to introduce that, yeah, it's quite easy to say landslide, but there is not only landslides. Of course, this is a general term that describes a wide variety of processes. They are, of course, related to the effect of gravity and to uh, um, uh, the presence of an instability along a slope. There is a very old definition of what a landslide is and what are the main landslide causes that I would like to remind, because I think that has been written many years ago, but is quite the best description that we have about landslide causes. So undercutting the foot of the slope, the deposition of earths of other material along the upper edge of the slope, and the average shearing stress of the potential surface of sliding becomes equal to average shearing resistance as landslide occur. So this is a very short description of what can happen to a slope that create a sequence of effect that can generate a landslide. Of course, there is a very incredible literature on this topic. I would like to remember is not very recent. There are many other texts more recent than this, but I think that this special report written by the U.S. Transportation Research Board can be an useful book and useful test for people that want to make a first analysis about the world of landslide. So have an introduction and a good description of what a landslide is and how we can manage these slope instabilities. Few words about the main elements that usually characterize a landslide. You see, this is a slope. From the upper part, you have a crown, and then inside the landslide body, we have different parts, some minor scarps, some cracks, and the toe and the foot and the toe of the landslide, they are the lower part of this slope instability. In some cases, damages are related to the presence of, I don't know, some buildings or someone else on the upper part, or in many cases, damages are related to the effect of the toe over the lower part of the slope, for example, the lower part of a valley. In the landslide classification, there are many different landslide classification, but probably one of the most common has been defined by Varnis in 1978, and then several updates, but more or less the classification is the same. And if you see, there are two different elements. There are the type of movement and the type of material. So if we consider the type of material, there are three categories that are bedrock or engineering soil that could be debris if there is a predominancy of coarse material, or earth if there is a predominancy of fine material. So bedrock, debris, and earth are the three categories of material. And on the other side, the other important element is the definition of the type of movement. Using these two elements, we are able to describe more or less all the landslide that we have all around the world. This is a simple description that is very useful because you have the possibility to see a very simplified representation of different kind of landslide. We start from in next slide. I will show you these different kind of slope instability. But in this representation, you can see that along different slope with different morphology, we can have different gravitational processes. This is just another representation. And then I would like to introduce the description of different kind of landslide. Since I will share this document, I don't want to describe all in details, but just to introduce that, of course, faults are a very dangerous kind of landslide because there is characterized by a high velocity, and in particular with faults, we are in many cases we have not many precursor elements, so it is quite not easy to know when the landslide will occur. This is a video. Please have a look in particular in the upper part of the. Okay. So this is a typical rockfall. You have like in this case, this occurred 2 years ago in close to Gallivaggio. In the lower part, there is a sanctuary that luckily has not been destroyed, but this is this rockfall. So this is an example of rockfall. So a very fast slope instability that can create many damages. Another kind of faults that can occur, and that is quite different in particular from the dynamic of the movement, is called toppling. This is another example of fault that characterize in particular the bedrock, and this is here another video because I believe that, sorry, I have to reduce the volume. So this is another example of faults. This is a toppling. You have seen the rotational effect related to the instabilities, and then the collapse of the most unstable part. These are the most impulsive phenomena that we have, and that are very dangerous again, because usually we are not able to find a good monitoring solution. So we are not able to know when and where this slope instability occur. Another kind of landslide are that characterize mainly not only the bedrock, but also debris or Earth's material, are rotational slides. In these cases, you can see there is a rotation, but there is not the rotation of toppling. There is another kind of rotation at the base of the shear surface, and then the landslide occur. In these slides, we can have a rotational plane on a translational landslide when you are not this, when you have a planar shear surface. Okay. There are many examples of these rotational landslides. Just to show you a very interesting case study. This is of course not a mountain case studies, but you can see in this slide the effect of the rotation due to the creation of this shear surface. Okay, this is another example, and this is a 3D model related to the a cross-section made on the landslide. You can see also in this case the effect of erosion made by the sea, because you have the position of the cliff profile in 2011 and in 2019. Okay. If we continue with other with other different kind of landslide. This is a good example. We are in Regione Piemonte in Lang Hills that are characterized by the sequence of deposits that create a favorable condition for the activation of these translational slides that are very quite famous in people that work on Landslide. You can see these very clear and plain shear surface, and then this translational slide can occur also when you have some weak levels inside your bedrock sequence, like in this case. Another quite interesting and not so easy to find type of landslide is the lateral spread. We have, this is quite common of different geomorphological environment, and in particular when you have a sequence of horizontal strata and when you have a sequence of soft clay strata. In Alpine Valley, we have some cases in these where this kind of landslide can occur. Here we are in the Aosta Valley, and this is and this is a landslide occurred more or less 20 years ago, and is related to the presence of a sequence of glacial lacustrine deposits with an high percentage of clay, and you have this landslide even if the inclination of the slope was quite low. This is probably one of the most interesting lateral spread that we have in the northwest of Alps. Are not so common, but the problem is that can occur also in the bottom of the valley, like in this case. If we continue, of course, this lateral spread can have many effects of infrastructure that are present in the bottom of the valley, and we would like to introduce the flows. So when we consider flow, we have different kind of possible debris flow, and in particular there is a very important slope instability that is called debris flow. Okay, so is a slope instability that has been classified inside the landslide classification, but then have a particular literature when is considered the debris flow confined by a channel. So in the case of a debris flow that is confined along a channel, along a stream, we have the possibility to see phenomena like this one. Sorry, this video has been taken from YouTube. We are probably in Afghanistan. You can see that we are close to the bottom of the valley. There is no rain, so seems to be a dry day, but then along this channel arrive what is called a debris flow. So a mix of water and debris, with also the presence of block of big dimensions that characterize many of the alluvional fans that we have in mountain valleys. So in my experience, debris flows are very often processes that are quite underestimated with respect to other slope instabilities, because very often I will present a case study occurred more or less 10 years ago. In many cases, these debris flow characterize also very small catchments, and in mountain area are unfortunately related with flash floods that characterize this particular period also as also because the implementation of the frequency of flash floods is considered one of the effects of the actual climate change trend. So this is the Garand debris flow case studies occurred in 2000. Sorry, no, it's not 18, it's 2008. This is an error. I took these images 2 hours after the occurrence of the debris flow. You can see this is the catchment and this is the alluvial fan where there were many construction that has been built more than 100 years ago. So are also old buildings, but in some cases, the presence of old buildings do not mean that the risk is low. This is a representation the day before the debris flow. You can see the presence of different houses, and this is an aerial view the day after the debris flow. So this house has been totally destroyed, and even these houses has been totally destroyed. And unfortunately we had 4 victims. But I would like to point out the distribution of rainfall in this area. There is the Pellice Valley. We are not far from Torino, so we are in Piemonte region. You can see that we have 3 different rainfall gauges, and the distribution of precipitation is very, very different. That means that we had a very, very localized effect that activated in particular these 2 different catchments, this one and this. And in this catchment, there is very close to Garen hamlet, we have this effect. You can see in these 2 slides, these 2 images in particular, the dimension of blocks, of rock blocks that are being moved by this mix of mud and water, and the effect of over an house. So when we started to remove the debris flow deposit, we realized that the first floor of the house was totally destroyed and filled by the debris flow deposit. On the contrary, the upper floor were perfect conserved. Okay, so this is an example of what occurred along the catchment when a debris flow arrived. And another critical element is the erosion effect produced by this movement of this mix of debris and rock block. So this is the top of the catchment when the debris flow started, and the debris flow starting with a small slide that involved in particularly the deposit over the bedrock. So at the contact between the bedrock and the deposit, we have an activation of a shallow landslide. So you can see that the depth of this landslide is more or less 2 meters, 2.5 meters. But with a positive feedback, an improvement of the erosion of the deposit along the catchment, the effect of the erosion improved the material that has been moved by this slope instability, and you can see the different level of the erosion created by the debris flow. So this is the man of this picture. You can see the different scale of the phenomenon. So what started with a simple small slide then ended at the lower part of the slope with a very, very, very big debris flow that has been able to kill 4 people. Of course, there are many other, if we move back to the landslide classification, there are other kind of flows that are usually less dangerous. There are the earth's flow and debris avalanches. There are the evolution of slope instabilities that in many cases are involving particular superficial deposits. In some cases, we have these debris avalanches. They are a sort of debris flow when these debris flow occur along the slope and is not channeled inside a stream. Okay. Of course, there are debris avalanches at different scale. This is a very, very big debris avalanches. In many cases, debris avalanches are related to the, again, to the activation of very, very small slope instability. So a shallow landslide that then move over the slope. This is an example of earth flow. Again, this earth flow characterizing mountain area, in particular glacial acoustic deposit, and that is why we can have this landslide also in the bottom of the valley and along slope that are very gentle, and that is why it could be dangerous because we are sometimes not able to recognize this possible hazard related to the possible activation of this kind of landslides. And this is a typical mud flow that occur that involve superficial deposit that you can see and at the base of the slope with this mud deposit. Okay. Of course, when we consider landslide, in particular for bigger case studies, we can have also what we call complex landslides. That means that, for example, they could start as a rotational landslide and then they could evolve like flows or in other using other dynamic. This is an example of a case study that Danilo Godone know very well, and this is an example of a complex landslide occurred in the south part of Italy, close to a town called Maierato. So you can see this video acquired during the activation of the landslide. You can see in the upper part, the landslide that is characterized by the activation of a very, very large rotational slide, but then the deposit, the evolution of the deposit is an evolution that make this slide so we can define this slide as a complex because in the upper part we have a rotational slide, but then it's quite clear that we can define this lower part as a flow. Okay, so this is the Maierato landslide. Danilo just shared a publication that he present over this landslide. There is probably a quite good example of what we call a complex landslide. You can see also that this flow is characterized by the total destruction of the original structure of the landslide body that at the end of the flow is characterizing by the heterogeneous deposit made by the original sequence of the upper part of the slope that has moved downward. Okay, so with this video related to the Mayerato landslide, I would like to finish the presentation related to the landslide classification and introduce a few slides related to another possible slope instability that we'll discuss in particular by Niccolò in the last part of our presentation, and is related to glacial instabilities. In particular, in many parts of the world, we have several hanging glaciers that can create a critical condition for the activation of big ice avalanches. This is the Wimper Serac. We are again in the Aosta Valley. This is the Grand Juras glacier, and just to make a very simple description, hanging glacier are glaciers that very often are characterized by the presence of morphological step of the bedrock. That means that you have the glacier in the upper part of the slope, and that you can have a morphological change that create a possible critical condition. So in this part, you can have the activation of different slope instabilities. When these slope instabilities are small, very often it is not a problem, but the problem is that when you have the activation and the detachment of a large volume ice, in this case, you can have the creation of what is called an ice avalanche. So an avalanche where the ice fall down and again could have a positive feedback effect with the erosion of debris deposits or even snow deposit that increase the final volume of these ice and rock avalanches. An example is the Kolka Carmadon rock ice lava occurred in 2002. And this is a video again taken from YouTube about the Turtleman Glacier, and the collapse occurred during this summer of that is related to the frontal part of the glacier. So this is what we can call an ice avalanche. It's not big, but of course, it is quite impossible to stabilize the glacier, and it is quite impossible to find a way to use active system for a reduction of the hazard related to this kind of slope instability. The only way that you have to reduce the risk of these processes is a reduction of vulnerability. That means a correct management of the elemental risk. I think that I don't know, Danilo, if we want to make the stop now or I can continue.
Right, we can stop now. I invite everybody, if there are some questions, they can write on the chat or can ask directly. And I would like to know if the audio issue is solved.
So of course this was an introduction in what we call landslide classification. Okay, great. You see, we have different kind of landslides. why is so important to define these different kind of landslides? Because different kind of land. Okay, so these different kind of landslide means different dynamics and means also different system that we can use to monitor these slope instabilities, or to find a way in some cases to stabilize the slope, or to create some infrastructure that are able to reduce the risk. How often this landslide occur during an year? Well, it is not easy to answer to this question. Okay, so to try to answer to these questions, the different kind of landslides have different frequencies. In particular, probably one of the most common landslides is rockfalls. So we have many rockfalls. You can just think about rockfall that can affect streets or infrastructure in high mountain regions. So probably the most common landslide are rockfalls, and the frequency of rockfalls is very high. If we consider, on the other hand, the risk associated with raw glaciers, yeah, it is not easy to define. So if we have, so the main risk of the snow glacier melting is the reduce of the ice inside the raw glacier. That means that we have a reduction of the fresh water that is inside the raw glacier. But on the other side, the raw glacier could be also deposit of material that could be activated for the generation, for example, of debris flow. That means that if you increase the instability of the deposit of the raw glacier, probably you can have the activation of other slope processes, like, for example, the activation of the debris flow that could occur involving also a part of the raw glacier deposits. So probably this could be a possible effect, that there is not a direct effect on the raw glacier, but where the raw glacier can be involved in other slope instability. Yes, there is a correlation between rain and landslides. Again, we use this landslide classification because the correlation is not the same for different landslides. So there is a clear correlation between shallow landslide, what we call shallow landslides and rainfall. And that is why if we want to manage the risk related to shallow landslides, one of the best way is to define some rainfall thresholds. But in particular, there is this very close correlation. So when you have strong rainfalls that occur on steep slopes, you can have the activation of these shallow landslides. Again, yes, the land use is important because different land use can create change the behavior of the slopes towards the same quantity of rainfall. Just to give you an example, one of the most critical elements that we recording during floods, and in particular during flash floods, is the effect of roads. So the cut of the roads is one of the point of the slope when we have an high frequency of activation of this slope instability. And also a correct management of the water that can be that can flow along roads is another important point that can reduce the frequency of activation of shallow landslides. So in particular for shallow landslides, there is a clear relation between the rainfall and also the land use. A correct land use, a correct management of the slope create the condition for a reduction of the hazard related to the activation of shallow landslide due to rainfalls. Okay, so the correlation between roads, there is not a real correlation, of course, between flash floods and roads, but in many cases, the presence of roads that create a sort of path for the flow outside the streams can activate many shallow landslides. So during a flash floods, if the presence of many roads very often can create a critical condition for the activation of more instabilities. Okay, that means that in terms of kind of adaptation, means that we have to be very careful in the cut of slope for the creation of roads, and we have to be very careful in the management of the water that could flow along roads during in particular during a flood, in particular during a flash floods. So if we are able to reduce the cut of slope for the creation of road, or during the construction and the maintenance of road, to work for a good stabilization of cuts made for the creation of roads, we can decrease the frequency for occurrence of shallow landslide that very often are quite dangerous, and in particular are critical because few of shallow landslide that have been activated by a flood along a road are able to close the road, for example, are able to stop rescue teams that have to, I don't know, reach the upper part of the valley where there are many problems. So again, an underestimated point is so I will also answer to this question. So in my opinion, and with Danilo, we also publish a paper on it, there is an underestimation of the effect of roads for the slope stability. And this is a very important point. So there is a strong connection between the slope stability, the present and the current maintenance of the road network and the land use. The study about the relation of mining so the relation between mining and mountains. there are many points they have to consider. The first is, of course, that mining create many deposits, and in our experience, even in Italy, these deposits are very often not so stabilized. So you have the possibility of the activation of very large slope instability that also could collapse and create a temporary dam breaks. So this is the most critical, most dangerous condition for the activation of very large debris flow. And these are landslide, and these are slope instability related to not correct management of anthropic deposits. And this is the first point. The second point, of course, if you want to mine a zone, you have to reach this zone, and that means the generation of a larger infrastructure that you have to create to reach this zone. This large infrastructure, that means roads, that means an area for mining, that means many deposits. This large infrastructure, of course, will change the stability condition, the environment. That means that this change in the condition can be used in sometimes to stop the mining activity, or I believe that is this mining activity have to be done, we have to ask that the mining company have to follow several limitation. That means that have to be careful about the environment, have to be careful about the temporary or the permanent deposits related to mining activity, have to be careful about the creation of roads, so have to be careful about several effects that are not related to the mining activity, but that can have also important impact on the environment, and they are very often are not considered in many national rulings that are considering mining that have some limitation about mining, but these rules are very often very concentrated on the on what we can use, for example, as like for chemical components that we can use for mining activity. In many cases, we are not so concentrated on also on secondary effects than the mining activity could have on the environment. We have, for example, we have the example in Aosta Valley where a very large and important mine of iron has been closed more or less 30 years ago, that during the last floods we had the activation of a very severe debris flow that occurred starting from these mining deposits. So the problem is that mining deposits could be a danger even after many years after the stop of the mining activity. And that is why we have to be very careful about the creation of these not consolidated deposit that along slopes could be very dangerous. I don't know if I answered to all questions. Yeah, probably yes.
Okay, Daniele, thank you very much. We are a little bit late, so if you don't mind, I would like to ask you if you want to continue till the next break.
Yeah.
Okay, so please.
Okay, I can continue. So I introduced the different kind of landslide that could occur along the slope, but of course this was just the beginning of this analysis, because the final goal, of course, is a correct management, as your question pointed out. The final goal, of course, is a correct management of this hazard. That means that we have to consider a strategy for a correct risk assessment of these slope instabilities. So we know that the climate change is also created new critical condition for the activation of these dangerous slope instabilities. We know that many human settlements in our mountain region create the condition for a high vulnerability of this area, and that means that we are we are improving the level of risk because we are increasing the level of vulnerability of this area. And this is a very, very critical point. So on one hand, we have the possibility to make new construction, to, I don't know, have new touristic activities, new touristic infrastructure, but we have to be even very, very careful, because since the environment is changing, they are changing also the slope instabilities. That means that in the evaluation of the risk, we have to know very well what has been occurring in the past, but also what could occur in the next future, and that is related to the new condition on the environment, related to, for example, the change of the level of permafrost, the activation of new slope instability, and so on. Of course, when we have to make a risk assessment, there are three main steps that are summarized in this flowchart. That are the risk analysis, the risk assessment, and the risk management. First of all, if we want to analyze an hazard, the first element is to know this hazard. That means, for example, the hazard analysis that is characterized by, of course, the landslide characterization and the analysis of the frequencies. And then we have to define the consequence analysis. That very, very often is one of the most critical points. So in this slide, you can find a sequence of keywords like landslide susceptibility, hazard, risk, also elemental risk, vulnerability, and zoning. And then here you have also the landslide susceptibility zoning, hazard zoning, and risk zoning. So this is an important point, because in many studies I had the possibility, I realized that sometimes the difference between susceptibility, hazard, and risk is not so clear. The landslide risk zoning is what we consider the final goal, but unfortunately, in many cases, we are not able to reach this goal, in particular because it's very complex, the definition of the vulnerability. That means the definition of the degree of the damage of the infrastructure that we have in the area that could be struck by a landslide. In literature, we have, on the contrary, many papers published for the landslide susceptibility zoning and the landslide hazard zoning. In this slide, I would like to present a sequence of action that you could do to obtain a landslide susceptibility zoning. So first of all, of course, you have to know the history of the slope that you are and of the area, not only the single slope that you have to consider. That means that you have to recognize and map ancient landslides. And one of the most easier solution for the identification and map of landslide are, for example, aerial photographs. So this is an example or very detailed geomorphological map of a single landslide. And this is a sequence of aerial images that can be used for the identification of the landslide and also for the identification of the evolution of the slope. This is another case study I published with Danilo and other colleagues. So this is the Champlain du Col landslides. Is not a very big landslide. This is the landslide that the most recent landslide activated I didn't remember, in 2018, so 2 years ago, that are relating to another critical moment, to another critical effect, that is the snow melting. So even the snow melting have sometimes have an important impact of slope instabilities. So this is the last landslides that has been also represented in this different aerial view, but you can see that this small landslide is only a part of a bigger landslide that we can recognize even in aerial images acquired 70 years ago. That means that in many cases along the same slope we have a sequence of landslides activated in different moments that can be also be a reactivation, a partial, a total reactivation of more ancient slope instabilities. Danilo will show some effect of the floods occurred in the few days ago. Just to give you an example of what we can do after a flood event. In 2014, we had 2 floods occurred more or less in the same area. This is the Liguria region, so this is the Piemonte. We are in the northwest of Italy. The most involved area in the last floods occurred Sunday. Was more or less here, so not far from the area involved in the floods of 2014. After these floods, we use our LiDAR system. There is an heliborne system to fly over the most critical area we acquire very large areas using this system. So the LiDAR, there is a system that is able to acquire both a sequence of photo of the area, but also a 3D model of the same area. In this representation, you can see the orthophoto of the area, but also two different representation taken from derived from the digital terrain model. There are this shaded relief and the slope map. Using this system, we were able to acquire an incredible number of landslides and to characterize the map of this landslide occurred in this area. In Italy, we have a national inventory that is called IPROMO. IPROMO means the Italian Landslide Inventory. That is a national project that has as a final goal the creation of this inventory. You see that the more than the 7% of Italy is covered by landslide. There is a very high number. We in this landslide inventory, we map an incredible number of landslide from rock slopes, sorry, for rock falls to landslide that involve all the slope. Of course, if you don't have aerial images, if you don't have the possibility to use LiDAR, there are other solutions, even cheaper solution that are relating to the use of remote sensing system. In this publication, there is an analysis of different approach based on different remote sensing system, like aerial photogrammetry and satellite images or laser scanner. Of course, there are also many different examples known in literature of automated or semi-automated identification of landslides that are not very easy, and these automatic approach very often are related to fresh landslides. So landslides occurred in last years. The use of automated system for the identification of ancient landslide sometimes, in many cases, is not so easy, and probably the identification done by a good geologist is the is the best solution. Of course, you can use aerial photogrammetry, satellite images, but also, yeah, in some cases, terrestrial laser scanning, so close range remote system, or spaceborne INSAR images. The SAR interferometry is a good solution, in particular, as I told you before, for active landslides. So you have the possibility to identify active landslide in different way, using the coherence of images, using, for example, what is called permanent scatterers. So there are the results of a sequence of images a sequence of SAR images that identify points that are characterized by a movement, and using this movement, you are able to detect the presence of landslide along slopes. When you define your landslide, then you have the possibility to, of course, create your landslide map, at different scale. Of course, usually the degree of detail of the landslide map is related to the scale of your map. In many cases, landslide maps, in many cases, landslide maps, in particular if the final goal is the susceptibility, are maps where you map not the geomorphological elements that characterize the landslide, but only the limit of the landslides. When you have a good data set, then you can use different methods to obtain your rockfall susceptibility maps. Just an example of these rock susceptibility maps. Again, this is a work that we submitted, Martina Cignetti, Danilo Godone, and me, and also some colleagues of the Geological Valley, the Aosta Valley Geological Survey. In this map, you can see the rock susceptibility along a regional road network. That means that we start from this IRPI project, so we have good database with a high number of records of rockfall occurred in area close to roads, and then using this data set and using information that we have, in particular the digital terrain model and the CARG project, the CARG dataset. So the CARG is the Italian project for the geological map. That means that we have the lithology map of the Aosta Valley at a very detailed scale, and also the land cover. So using all these material and combining this material using this analytic hierarchy process, we can obtain the susceptibility map that I show in this image. This is an important final goal because at regional scale, you can have the map of the area that could be characterized by a different level of susceptibility related to rockfalls. Another example and another approach, not so different with respect to the previous one, is presented in this publication. So we started from the data set that we acquired after the mapping of events occurred during the floods of 2014. You can see these events that are these red polygons inside this catchment. And then we have also many records from the Italian landslide inventory, the IRPI project, of shallow landslides occurred before the 2014 in this catchment. And in this case, since we are considering non-rockfalls, but we are considering shallow landslides, that means that we are considering landslides that are activated in the deposit over the bedrock, so in the deposit that very often are 2 up to 3-5 meter thick. So in these cases, using a quite similar approach, we combine data derived from our LiDAR survey. That means that we combine data related to the slope, the aspect, but also the lens view, the lithology, and using these data and combining this data with the shallow landslides data set of 2014, we were again able to define this shallow landslide susceptibility. So we reach what is the first step to that is necessary for the definition of a landslide risk. Okay, then I believe that in many cases this is not the final goal, this is not the best goal, but this is a very important results, because you have the first characterization of your environment. So this is a result. The other one is this map, and inside these two maps you have the possibility to have an evaluation of what is the susceptibility of your environment towards a different kind of slope instability. Starting from this point, then you can obtain another map, but in particular a risk evaluation. You know that, as I mentioned before, the final goal, so the risk assessment, is a product that consider not only the hazard, so not only these results, but also that they have to consider also the vulnerability of the infrastructure and the elemental risk that you have in this area. And unfortunately, this is not quite easy, and that is why in many cases the studies stop with susceptibility, do not reach the final goal of a real risk assessment, in particular a regional scale. If we consider, on the contrary, an approach at local scale, so at the scale of the single landslide, at the scale of the single landslide prone area, then in these cases it's quite easier to define clearly and to clearly recognize the element of risk. I don't know, the presence of 1, 2, 3 houses, the presence of a road, the classification of roads in terms of both vulnerability, but also in terms of the cost or the value of the roads. That of course is different if we consider a motorway of a very local road. So at the regional scale, in many cases, the final goal is this susceptibility map related to a particular landslide typology. On the contrary, at the local scale, the final goal could be the a risk analysis. Then, few words to finish my presentation about the risk mitigation. That is, at the end, the final goal. So we realize that we have different kind of slope instability. We realize that this different kind of slope instability is characterized by different dynamics, different activation. In some cases, there is a clear relationship between rainfalls. In other cases, there is and the activation of landslides. In other cases, there is a clear relation, for example, between snow melting and the activation of landslides. But then the final goal, of course, is the risk mitigation. Risk mitigation, what does it mean? It means the definition of scenarios, okay, they are created at local or regional scale. In particular, if we consider the local scale, the design and the mitigation of this measure could be the base for the creation, for example, of early warning system. And early warning system are systems that are based on the use of monitoring solution. The easier monitoring solution are, for example, for shallow landslides, the presence of rainfall gauges that are able to acquire the quantity of rainfall, and if you are able to define rainfall thresholds, you can link you can link these thresholds to the probability of occurrence of the landslides. Then inside this scenario, as I told you before, an important element is the estimation of the potential loss of all the elements of risk inside this scenario. So you start from the identification of the landslides, its kinematic, its volume, and the characteristic in terms also of runout.
मैं आपको बताऊं, देखो कोई भी ऐसा दिन नहीं है जिस दिन आपको ज्यादा ट्रैवल हो। पहले दिन है 6 घंटा, दूसरा दिन आपका केवल 1.5-2 घंटे का ट्रैवल है।
Please.
तीसरे दिन आपका 5 घंटे का ट्रैवल है। फोर्थ डे भी 5 घंटे का ट्रैवल है।
Mic is on. Somebody's mic is on.
सेवेंथ डे आपका 3-4 घंटे का ट्रैवल है।
I'm sorry, but I'm not able to find.
5 घंटे का ट्रैवल है।
No, me too.
जोशीमठ से बद्रीनाथ 2 घंटा है, फिर श्रीनगर।
Daniele, sorry, I don't know who's speaking because of them are stop. I don't know.
That's the point.
Someone from another virtual classroom. I don't know.
Okay.
Stop. Yeah, I think we could go on. Yeah.
Yeah.
So
sorry, Daniele.
No, don't worry. Sorry. So we are discussing about the local scale and the local scale approach. That means we start from the definition of what could happen, and then we recognize the landslides and the probability of occurrence. Then, when we have estimated the volume and in particular the runout distance, we are able to define the scenario, and the scenario is the base for the estimation of loss of elemental risk. And at the end, when we have this scenario, when we are able to define the risk assessment, then we can decide if the level of risk that is related to the scenario could be considered accepted or not. Because you know that in mountain areas it's not so easy to have a risk zero, and that means that we can also define what is the acceptable level of risk. This is very often one of the most critical points because it's not so easy, in particular from the political point of view, the definition of what is considered an acceptable risk level. And then, once we have defined what could be considered an acceptable risk level, then we can define and implement some risk mitigation strategies. That means, in several cases, find a way to stabilize our slope, or find a way to create some infrastructure that are able to, I don't know, to stop or to change the runout direction of our slope instability processes. Okay, sorry. And I don't know if I have the time to introduce another topic or we can stop here. I have some slides related to the monitoring activities.
You can go on 10 minutes.
Okay, so just to introduce one of the last part of the topic that I would like to present. So we recognize the presence of the landslides, and then we have we have to find a solution, for example, to monitor the landslides. if we are not able to stop this slide. So that means that we can use several monitoring systems to recognize the movement of the landslide and to characterize its landslide evolution. Of course, now when we think about landslide monitoring, we are considering not a qualitative approach that is able only to recognize the movement, but we are considering in particular a quantitative approach that is able to measure the deformation. Inside this process, there are we are able to monitor in particular the superficial displacement, the deep displacement, or other parameters like, for example, the rainfalls. Just to introduce very fast several solutions for landslide monitoring, one important point is that when we use this question, the first point is that we have to define the better solution with respect to the question. So we have to start from a question, then define the strategy. And this is a typical scheme that we can use for the definition of a landslide monitoring network. So in this simplified scheme, you have the presence of the shear surface, and then the use of different systems that are able to acquire different parameters. Like I presented before, the presence of a rain gauge, okay, that is able to acquire the quantity of rainfall that fall down in this area, but other important elements are sensors that are able to acquire the slope movement, like this, that is an extensometer, but also the pore pressure inside the slope. The pore pressure is an important element because in many cases the activation of the landslide is directly related to an improve of the pressure inside the slope. I don't know if you are able to follow because scusami Danilo, io vedo
you can stop for a while. I'm trying to find out. So may I have your attention, please? Excuse me. Everybody is excuse me. Everybody is kindly requested to stop using the microphone. Okay? Please. If you need to make a phone call or other conversation, go away or switch off your microphone. Thank you so much. Or I will expel you from the virtual class. This is my last request. Then I will act. Okay? Thank you, Daniele. Please.
Sì. Controlla perché c'è uno che è l'ultimo che
ma non riesco non ha il microfono, non ha l'icona.
Ah, ok.
Sì, Danilo, perdonami, penso sia proprio l'ultimo della lista. Adesso
lo temo anch'io.
fare nomi e cognomi. Cerchiamo di risolvere.
So I'm quite at the end of my presentation. This is the scheme that I would like to introduce. So in this cross section, you see that you have the possibility to measure all the main parameter that we can consider for a slope monitoring and the landslide monitoring. There are the superficial slope movement represented in this case by these crack meters. The pore pressure, and this is, as I told you before, this is an important point because This is an important point because in many cases, the activation and the entities of movement are related to the pore pressure inside the slope. And then, of course, other parameter like the rain gauge. Just to show you some example, this is another representation of the slope. You can see an example of what happened when a slide starts to move. So you have the crown of the slope, the crown of the slide on the upper part of the slope, the presence of several cracks, and inside the cross section you can see the shear surface of the landslides. This is the landslide toe, and the effect, like in this case, on a road related to the movement of the landslides. And then you can have, like in this case, the possibility to drill a borehole and to measure the deep displacement inside the borehole, and measuring the deformation of the borehole, like in this case. If we want to measure, for example, the superficial displacement, a possibility is the use of some topographic instrument, like in this case, that is a total station. There is a topographic system to measure the position and the change of position of several points, of several benchmarks installed on our slope inside our area of interest, to define the displacement of these benchmarks that are related to the movement of the slope. So you can see that for the monitoring of a simple case study like this slope, you have the possibility to use different monitoring system and a different monitor approach that are related to the monitoring of the displacement, the monitor of the superficial movement, but also the monitoring of effect. Like in this case, that you have the possibility to use tilt meters. Tilt meters are sensors that are able to measure the change of the inclination of elements, and they are very good, for example, for the for monitoring walls, side walls of roads, or also other buildings. And in the upper part, the other element that are good example very often used in landslide monitoring are crack monitoring points. So you have the possibility to monitor manually or automatically the distance between, for example, 2 points like this one, and to use the change in the distance for the definition of the opening of these cracks that you could have in the upper part of the slope that are related to the presence of the crown of our landslides, or in different part of landslide that are considered as secondary cracks, very often related to the presence of different kinematic domains inside our landslides. Okay, so this is, I don't want to make a detailed description of monitoring system, because this could be another lesson, and also because the next talk made by Niccolò Dematteis will focus in particular on some monitoring approach, but this is just to give you an idea of what monitoring or what landslide monitoring is. I don't know, Danilo, if we want to stop now and have some questions, or
yeah, we can stop now the lecture for some questions. Then we will stop for 5 minutes for a coffee break, and then we will start with Niccolò Dematteis' lecture. So please, if there are more questions, feel free to ask now.
Okay, so in this second part, I try to introduce several elements. The first one is that when we know what a landslide is, then we have to find a solution to manage this critical condition. And to manage this critical condition, the final goal very often is the definition of the risk assessment related to landslides. There are many steps that we have to do to reach this final goal. And first of all, landslide mapping is one of the most important points, because we have to know. No, sorry, probably I was not clear. Is not so it's easy to do a vulnerability map at regional scale. It's not easy to do a risk map at regional scale, okay? Because to obtain a vulnerability map, you need a good data set of your kind of landslide that we are considering. I presented two different examples.
Daniele, we lost your connection. Daniele, can you hear me?
Danilo.
Okay, I have an update. The computer of Daniele has crashed now because Niccolò Dematteis update me. So it's time for a 5-minute break. Sorry for this inconvenient, but so we will have time to change the lecturer. So we will see you in 5 minutes.
Yeah, and Danilo, if I could add, we postpone